Okay, so that was this example. All right, let's do, see if we did that. Here we go. Okay, so far we've done the probability of A and B. So one event and another event, right? One event and another event. What about or? What if we want the probability of A or B? You know, event A or event B occurs. Well, that's where this comes in. That's how we handle it. This is how we handle it. Okay? This is how we handle it. Basically here, let me just say though that when we say or in mathematics, we allow the possibility of both. So we include the possibility of and, so to say. You know, it's not like when you're talking to someone, you know, in conversation, I guess, where if you ask your friend, or your friend asks you, let me say it that way, where do you want to go for lunch, Moe's or McDonald's, right? Well, you're not going to say both. I don't think you're expected to, right? You know, usually if someone asks you if you want to go to lunch, Moe's or McDonald's, you're not going to say, well, let's go to both, right? You're not expected to say that, so to say. In math, however, both is a possibility. Both is a possibility. So I guess mathematically speaking, going to Moe's and McDonald's would be a possibility. But in everyday conversation, it's not expected that you're going to say, let's go to both. So just letting you know, here we allow both possibilities. It turns out to get the probability of both events A and B occur, of A or B occurring, we have this formula. Okay. Now we have the probability of A plus the probability of B, and we have to subtract the probability of A and B. Now, you might be thinking, wait a minute, why are we subtracting? Isn't the sum enough? Well, no. What can happen is, as I write down here, you could have overcounting, and we want to subtract that because we don't want to take a chance of overcounting. And that can happen, as my next example illustrates. So here, you know, we want to subtract to make sure we don't overcount. For instance, let's suppose we consider the experiment, where we flip a coin and we roll a die. Okay, we flip a coin and we roll a die. A standard six-sided die. Let's find the probability the coin lands heads up, you know, getting a head on the coin, or rolling a 6. So here we're calculating that by just looking at the sample space. Okay? That's what we're doing. So which outcomes are of interest to us? Well, we have these 6, right? Remember, we want the coin to land heads up. We want to get a 6 on the die or both. So these 6 are included, right? And we include this. You know, these take care of the coin. These come from the coin landing heads up. This, however, comes from rolling a 6. But notice this event here, H6, would be in both outcomes. Excuse me, this comes from both outcomes, so to say. You know, this here you can obtain from the coin landing heads up. The 6 here, this 6 tells us it comes from rolling a 6 on the die. So if you're not careful, you might list this twice, H6. So think of it this way. If we allowed repetition here, right, in a set, H6 would be listed twice because it comes from the coin landing heads up and it comes from rolling a 6 on the die. We don't want that listed twice, right? We don't want to overcount. So that's why we have to subtract. We'll see that in the next slide. But the answer you can see here is 7 out of 12. Yeah, I hope I'm explaining it well. I'm pretty confident I am. But the probability, as you can see, is 7 out of 12. Okay. Now let's actually use that formula. Okay, so I know it's kind of silly because we have the sample space, but it's still good to know how to use the formula. You know, you're not always going to be able to get the sample space. Now, we're going to let A be the event. The coin lands heads up. Maybe we can say it there, but I'm saying it here. So A is the event that the coin lands heads up. B is the event we roll a 6. Okay, so what would event A look like? Well, the outcomes in it are these. You know, we have H1, H2, 3, 4, 5, and 6. You know, the coin lands heads up. And so the probability of A is 6 out of 12, which is a half. Same thing. Now, for B, right, that's from rolling the die and getting a 6. What do we get there? Well, what outcomes correspond to that? We have H6 and T6, 2 of them. So this probability of event B occurring is 2 out of 12, 1 out of 6. But now you can see, well, if we just add them, this outcome, H6, is being counted twice. And we don't want to count it twice. Then our answer is going to be wrong. That's why we have to subtract it. Now, how can we formally subtract it? Well, H6 is the probability. H6 corresponds to the event of A and B. That corresponds to event A and B. In other words, the probability of A and B is 1 out of 12. Okay? A and B corresponds to that outcome that's listed more than once. So we subtract it. That's what we're doing here. And I'm using a formula. And you can see that, yeah, we get 7 out of 12. Okay, that's good. Okay. So that's why. So again, that's why we subtract. Mostly because, again, we don't want to count an outcome more than once. We don't want to overcount. Okay, so these events, A and B here, had something in common. I mean, if it happened to be that A and B had nothing in common, then we can just add. That's the idea of mutually exclusive. In other words, 2 events are mutually exclusive if they have nothing in common, no outcomes in common. In other words, their probability is 0. Excuse me, the probability of A and B is 0. So they both can't occur at the same time. That's what I'm saying. Yeah. If A and B are mutually exclusive, so in other words, this happens, it's pretty easy to get the probability of A or B, at least in theory. Or you just get the probability of A and the probability of B and add them. You don't have to worry about not overcounting because there's nothing in here. It's just something to consider. Okay. All right, that's what it means to be mutually exclusive. Okay, well, let's do an example or two with that. So here we have a standard deck of cards. Remember, there's 52 cards there. Okay, no jokers. We're drawing a card at random, just one. You want the probability that the card there is an ace or a card from the suit of clubs. So again, it's an ace or from the suit of clubs. Okay. Well, what I'm doing is this. I'm going to let A be the event. The card is an ace. I'm going to let B be the event. The card is from the suit of clubs. So A is the event that the card is an ace. B is the event the card is from the suit of clubs. So the probability of A, what is that? Well, there's 4 aces in the deck, right? That's 4 out of 52. How many clubs are there? How many cards are there from the suit of clubs? Well, each suit has 13. So there's 13 out of 52. Okay? What's the probability then of A and B? Well, how many aces in other words, how many outcomes are in both events? Well, how many aces are there in the suit of clubs? There's 1, right? There's only 1 ace in each suit. 1 out of 52. That's the probability of A and B, 1 out of 52. Because of that, the probability of A or B is, we're using this formula. We have 4 out of 52 plus 13 out of 52 minus 1 out of 52. These are not mutually exclusive. Okay, they're not. So we have this. Remember, when you add and or subtract fractions, you get a common denominator. We have that already. So you only add or subtract numerators. And we get 16 out of 52.